A planet moves through the galaxy completely alone. No sunrise ever reaches its surface. No reflected starlight flashes across the darkness. No bright system surrounds it. From a distance, there is almost nothing to look at. The planet keeps moving, but every familiar landmark is missing. Point a detection screen into that region of space and almost nothing appears. The object gives off almost no visible signal. There is no nearby star drawing attention to it. No obvious sign that a planet is even there. And yet the planet is real. It exists. It travels. It occupies space, but it is disconnected from the tools that normally lead us to planets in the first place. That is where the assumption begins to break. Planets do not actually need stars to exist. Some travel through the galaxy without orbiting any host star at all. A planet-sized world can drift across interstellar darkness with no sunrise, no reflected starlight, and no visible system around it. Once the star is gone, astronomy loses its most useful reference point before the search has even begun. This is not just a theoretical possibility. Studies of rogue planet populations have already produced multiple candidate worlds through indirect observations, which raises a much larger problem. If a planet can exist while remaining almost completely detached from the signals astronomers usually rely on, then a real world can be out there, moving through the darkness, while our instruments pass right by it. And if that is true, how much disappears when the star disappears too? A search begins with the assumption that the usual tools will work. A monitoring screen waits for a tiny drop in starlight. The graph stretches forward. The line never moves. The system keeps watching. Nothing changes. So the search shifts to another method. Measurements begin looking for the subtle motion of a star being pulled back and forth by an orbiting planet. New charts appear. Fresh data arrives. The lines stay empty. Again, nothing changes. The problem is not that the signals are weak. The problem is that the signals never existed. Most known exoplanets were discovered through the behavior of stars. A star briefly dims. A star slightly wobbles. The planet reveals itself through the effect it has on something brighter. But around a rogue planet, there is no host star to dim. The transit graph stays flat. There is no host star to wobble. The measurement charts remain empty. And the consequence is immediate. Two of the most successful systems in modern exoplanet detection stop producing useful results before the search can really begin. The detection pipeline does not struggle. It effectively shuts down. What looked like a difficult search suddenly becomes a different kind of search altogether. Entire categories of objects can slip past the methods humanity relies on most. Not because they are small, and not because they are far away, but because the measurements being monitored simply do not exist. The safe assumption is gone. A rogue planet is not just another exoplanet waiting to be found. The moment its star disappears, so do some of astronomy's easiest and most productive ways of finding it. The question now is whether anything can take their place. A dark field of stars sits unchanged. Nothing moves. Nothing stands out. The search appears to be back where it started. Then, one distant point of light suddenly brightens. Not by much. Not for long. But it brightens. For a brief moment, a tiny flash appears where nothing unusual existed seconds earlier. Then the star fades back to normal, as if nothing happened at all. The event is over. The data is not... Analysts trace the brightening and find that it matches a prediction with remarkable precision. something invisible crossed the line of sight. Something with gravity. The object itself never appeared. No glowing surface emerged from the darkness. No planet became visible. Yet the background star brightened exactly as expected. That is the breakthrough. Gravity can reveal what light cannot. A rogue planet passing in front of a distant star can briefly magnify that star's light. The planet remains hidden, but its gravity leaves a measurable effect behind. And suddenly, there is a fingerprint. A world that seemed completely detached from observation produces an observable signal after all. The search is alive again. Within microlensing detections, an invisible object can announce its presence without emitting meaningful light of its own. A distant star brightens. The measurements match. Analysis points to a planet-sized lens crossing the line of sight. For the first time since the star disappeared, discovery looks possible. The missing light no longer feels like a fatal obstacle. If gravity can substitute for light, then these hidden worlds may not be beyond reach after all. At least, that is what it seems. The signal reaches its peak. The distant star shines brighter than before. The measurements line up. The hidden planet seems caught. Then the alignment begins to drift apart. The brightening fades. Minutes, days, or weeks later, the star looks completely ordinary again. Astronomers return for another look. There is nothing unusual to see. The signal that revealed the planet is gone. The object that triggered the discovery has not disappeared. The opportunity has. Follow-up observations point back to the same location, but the brief geometric arrangement that created the event no longer exists. The brightened star returns to normal. The rogue planet vanishes from observation once again. That is the catch hidden inside the success. Microlensing depends on rare alignments. The event works because objects briefly line up in exactly the right way. Once that alignment passes, the lensing event ends with it. And so does the easiest access to the planet. A detection has been made. A discovery has occurred. But discovery does not become control. If microlensing had fully solved the rogue planet problem, each detection would become an observational target that could be revisited again and again. Instead, the opposite often happens. The signal appears, the alignment breaks, the evidence remains. The event does not. Within the limitations of microlensing surveys, many detections become effectively one-time observations. Verification becomes harder. Long-term study becomes harder. Repeated observation becomes severely limited. The breakthrough still works. But the promise has changed. We can uncover rogue planets. We can catch brief moments when hidden worlds leave a visible fingerprint. What we often cannot do is hold that window open once it closes. And that raises an even deeper question about everything still drifting unseen beyond it. A catalog of known planets fills the screen. Dot after dot appears across the galaxy. Confirmed worlds, recorded worlds, counted worlds. Then statistical models begin adding more. The map expands. New points spread into regions where no detections exist. The estimated population grows far beyond the list of directly observed planets. And the gap becomes impossible to ignore. The number suggested by observations is larger than the number we have actually seen. Much larger. Recent statistical models and microlensing surveys point toward a terrifying reality. Our galaxy may be drifting with trillions of rogue planets. They might outnumber the stars themselves by a factor of 20. That difference is the consequence. Our inventory of planets may not be missing a few entries. It may be missing an entire population. The limitation is not simply telescope power. Within microlensing surveys, discovery rates are constrained by rare alignments. Geometry decides when a hidden world briefly reveals itself. If the alignment never happens, the opportunity never arrives. Which means reality is not obligated to appear just because we are looking. As future missions like the Nancy Grace Roman Space Telescope prepare to scan the darkness, the goal is no longer finding a single rogue planet. The goal is measuring how many have been escaping notice all along. Because the deeper implication reaches beyond rogue planets themselves. Scientific understanding is only as complete as the methods used to observe reality. And when the easiest planets to find are the ones orbiting bright stars, a troubling possibility emerges. We may not know where most planets are. We may only know where the easiest planets are,